So we're going to do part I together for both A and B, and then I'm going to let you try to prove them, because this is a unit that no amount of watching, like, it will help you to watch someone else do a proof, but until you try it on your own and find out where your skills are and stuff like that, and just go through things, you're not going to learn very much from it. So I'm going to give you some time to try those. I'll show you a couple of proofs as a result, but we're going to start with the non-permissible values. So non-permissible values, some things there's non-permissible values, like tangent can't be pi over 2 and 3 pi over 2, because then you would be dividing by 0, and that's bad. But other ones, for secant and cotangent, or wherever there's a fraction, you're going to have to look to see if it's ever equal to 0. So for part A, okay, cotangent theta has a couple of things that aren't allowed. What's that? Oh yeah, homeworks for the last one, sorry, are 3, 5, 6, and 7 II. So for example 1, 3, 5, 6, and 7 II. After a while, I don't get you to verify because you're going to mostly be proving. So for part A, cotangent theta is the same as cos of theta over sine of theta. So we can't have sine of theta equals 0. That would be bad. So for tangent and cotangent, we need to look specifically at them because they have some non-permissible values. So when is sine equal to 0? 0, pi, and 2 pi, so those would be bad. Okay, we're going to solve between 0 and 2 pi first, and then go from there. Okay? I'm dividing by cosecant here, so it would also be bad if cosecant of theta were equal to 0. Now we're going to find out that cosecant of theta is never equal to 0, because if we change cosecant of theta to 1 over sine theta and multiply this expression both by sine of theta, we get 1 equals 0, which doesn't happen very often. In fact, it's not possible. So cosecant is never equal to 0. And you're going to learn this more later too when we graph cosecant, secant, and cotangent, and we learn about their domains and ranges, that cosecant is never equal to 0. But for right now, this is how we could show it. Cosecant is 1 over sine, and a fraction, the only way a fraction is ever equal to 0 is if the numerator is equal to 0. That's the only way a fraction can equal 0. And if the numerator is always 1, we'll never have that fraction equal 0. So the only problems here, theta can't equal 0, pi, and 2 pi, but that's only from 0 to 2 pi. This question said determine all the non-permissible values, so we would need to list all the ones coterminal with that. And the way that we could write that is theta can't equal, can you see that I'd have 0, pi, 2 pi, 3 pi, 4 pi, 5 pi? So we can write that as k pi, where k is an integer. If you wrote all three of those plus 2k pi, where k was an integer, like we did before, that would be fine as well. But I think you can start to see the shortcut for 0, pi, 2 pi, 3 pi, and just write that as k pi. So there's our non-permissible values for part A. Let's do our non-permissible values for part B. And our equation is cos theta, 1 plus cos, plus secant theta. Double check that. Okay, we don't have any cotangents or tangents, so we don't have to worry about those ones. The only place that we're dividing is right here. Whoa. That's the only place that we're dividing. So it's only bad if 1 plus secant theta, that can't equal 0. Well, what is that asking us? That's asking us to check when is secant theta, if I move this over, equal to -1? Well, secant theta is related to cos. This is 1 over 1, so cos of theta would be 1 over -1. Of course, that's the same thing. And we have to ask ourselves, is cos of theta ever equal to -1? Yes. It's equal to -1 at pi. Now, for your work, if you had the line through here, like all the way through, that's fine. Or if you solved it with an equal sign all the way through as just part of your work, I need to find out where 1 plus secant theta equals 0, because that's bad. Now, as far as your final solution, the non-permissible value then, theta can't equal pi, and then we have to list all the coterminal ones with that. So those are our non-permissible values. And now I'll give you some time to try to prove those two. Another thing in this question, you know that secant is 1 over cos. So that would be another place that you're dividing. So that also tells us that cos theta can't equal 0. So where is cos theta equal to 0? At pi over 2 and 3 pi over 2. So you could write both of those ones plus 2k pi as well. Yes. And these ones, you could put them together, but I'll just list them separately like that. So then our final answer for non-permissible values are all of these ones and all of those ones. Yes? Mm-hmm. What I did in A is I just looked at the equation and I looked if there was any cotangents or tangents, because they have non-permissible values. And I saw there was a cotangent, so that's why I wrote this. Because cotangent is equal to cos over sine. And then this implies sine theta can't be 0. Okay? And then I solved that little non-permissible value. Then I looked if I was dividing anywhere else, and I have cosecant. So I check if cosecant's ever 0, because I'm dividing by that. I should also write, cosecant theta is 1 over sine theta. So that would be another thing to check. But I've already solved that here as well, because that would also imply that sine theta can't equal 0. So we're just looking for all of our reciprocals, because they'll have non-permissible values: secant, cosecant, cotangent, and tangent. And we're also looking for everywhere where we're dividing by 0. All right, let's just check how you did. Again, a strategy that works out really well is changing things to sine and cos. Cotangent is cos theta over sine theta. And cosecant is 1 over sine theta. And I have a fraction divided by a fraction, so then I can multiply by the reciprocal, Yes? That's fine too. So that, like I said, there's many different ways that you can change things around. You could have said, well, I have 1 over cosecant here, so I could change 1 over cosecant to sine theta, and then work from there as well. For the second one, again, draw a line to separate the left side and the right side. I have cos theta on the left. I can change secant theta to 1 over cos theta on the right. I get a complex fraction with a fraction inside of a fraction. So my strategy is to get a fraction on the top and a fraction on the bottom. Now, I can get a fraction on the bottom by multiplying by cos theta and cos theta. I can get a fraction on the top by thinking, well, this is 1 over 1 and this is 1 over 1. I could, if I wanted to, write the whole top as a fraction over 1. Sometimes, I mean, it's not necessary to write that, but sometimes this question gets hard because people don't see that. That makes this a fraction on the top. On the bottom, I would have cos theta plus 1 all over cos theta, which gives me a fraction divided by a fraction. When I multiply by the reciprocal, I'm going to group these together because they have a plus sign in between them, and I hope you can see that they're the same. And because they're the same, you can simplify those and you just have cos theta. So therefore, my left side is equal to my right side. And we're done. So again, I use the strategy of getting everything with cos and then getting a single fraction. That is the most common strategy, getting things to sine and cos and getting things to a single fraction. Okay? That doesn't mean you can't be creative. Like in this one, you want to see a creative one, just as something different. Okay? You know that when you multiply by 1, you don't change anything, right? Okay? So if I multiply this side here, cos theta, and I multiply it by 1, that doesn't do anything. Now, writing a big 1 really doesn't do anything. But if I decided to multiply it by 1 plus secant theta and 1 plus secant theta, that would still be multiplying by 1. How do you multiply fractions? You multiply the bottoms, well, that's 1 plus secant theta. You multiply the top by distributing, this will become cos theta, and cos theta times secant theta is just 1, and I'm done. They're the same. Left side is equal to the right side. That was pretty quick. Yes? You could also factor out, a cos and then things simplify out. So there's many different ways and this is where you can be creative if you want to. I have given this strategy a name, which I call build the other side. If you're stuck and things don't match up, you can just build the other. You want a 1 plus secant theta on the bottom? You make a 1 plus secant theta on the bottom, as long as you're multiplying by 1. Okay? Sometimes, though, when you build things up, they get really complicated, and they're not necessarily seen as the nicest proof. What Florian was saying here is we could look at the right side and another key strategy. So this strategy I call build the other side. That's not patented yet or anything, so you can. Another key strategy over and over again is factoring. So if you factor out a cos theta, well, if I take a cos theta out of a 1, I get a 1 over cos theta. Because cos theta times 1 over cos theta is 1. If I take a cos theta out of a cos theta, I'm just left with 1. And on the bottom, I have 1 plus secant theta. If you see that 1 over cos theta is secant theta, these two are the same. And then we just get cos theta, and that would match with our original left side. So you have all of these different options for proving, and they're all right, and there's no deductions for long proofs or short proofs, as long as in the end you can make the left side equal to the right side. And that comes with practice. Okay, the questions for this one are 4, 8II, 9II, and II, or 11. The reason I don't give you the first I is that's the ones that are all the verifying and tedious work. So you're just working on proving.
So it's 4, 8, 9, 9,
11.
Confusing with II.
Sorry.